Okay, so in the last class we had seen how a flow can be turned isentropically with when without having an oblique shock or the turning compression waves. Okay, now we have derived rigorously how the entropy is 0. Now we are going to extend that and see how we can turn the flow, which is what we call as the expansion turns, and we see how the waves are being generated. So, what I would do here is when you have a turn like this, we had seen when the flow makes a very small turn d theta at each of these locations, we have derived how the entropy is going to 0. Entropy approaches 0 as d theta goes to 0, and the shock angle approaches to your Mach angle. Okay, this is what we had seen. Now what we are going to see is if something like this happens, and at every location there is a small turn d theta, what happens to this flow? Okay, so this is something, this is a compression, this is an expansion. Okay, so we will start by drawing the velocity diagram and see what exactly is happening in these two cases. So we will, instead of drawing these things, we will draw a small turn with one wave. So I have a flow with a very small turn d theta. So I have a wave that is approaching my Mach angle. So this is mu. So the turning is a very small turn angle, which is d theta. Likewise, I have a turn the other way around. So this angle is a very small turn d theta, and I have a wave here. This is my mu. Okay, so this is compression, this is expansion. Here my m1, m2, and my m2 is less than m1. Here I have m1, my m2 is greater than m1 because it is an expansion process. This is clear when you draw your velocity diagram. So I have a V tangential, this is my V1. So before the wave is 1, after the wave is 2. So I was cautious enough to say not shock here, just a wave. So before the wave is 1, after the wave is 2. So I have V tangential and then the velocity, resultant velocity, and if I draw 90 degrees from there, this is my V normal, V1 normal. Okay. So in a compression wave, the velocity would be because the turn angle is this way, the velocity, resultant velocity V2 is less than V1. Okay. Whereas when you come to this kind of turn, so I have a V tangential V1, 90 degrees from here is my Vn, this is my V tangential, and the turn is the other way around. So, I have a small d theta so this velocity V2 is larger than V1, okay. Hence, you are going to have a M2 greater than M1, here M2 less than M1, okay. So, there is always an increase in your velocity when you make a turn like this. So, in a compression wave, this is typically assumed negative and this is assumed positive, okay. The importance of which we will see it later, okay. For the time being, it is just the modulus of d theta. In one case we have an expansion, in another case we have a compression, okay. Now, we look at this particular triangle and try to see what we can get, how can we get this turn angle. If I know the Mach numbers before and after the wave, can I get a turn angle, is what we are going to derive, which is what we call as Prandtl-Meyer function, okay. So, the difference in Prandtl-Meyer function before and after the wave will give you the turn angle, okay. So, we are going to derive this. We will look at this particular triangle. I will draw that here and then try to deduce what is the Prandtl-Meyer function. V tangential, Vn, this is V1, and I make a small turn d theta, I get V2. This is my wave angle or the shock angle as we had described in our oblique shock, which I call it as mu, because that is now our Mach angle, and this is d theta, not theta. Okay. So, let me check the notations. So, I would write V2 as V plus dV, and V is V1 is V, okay. This is my 90 degrees. So, this is V1 normal and this whole length is V2 normal. V tangential is the same as we had seen in the oblique shock, okay. So, now looking at this triangle, so V1 is before the wave, V is before the wave, V plus dV is after the wave. Now, from looking at this triangle, we can write V3 is cos mu of your V, okay. So, it is just the cos of this angle, okay. Vt is also this angle and component of this. So, it is V plus dV into cos mu plus d theta, okay. So, cos nu plus d theta is multiplied by this is your Vt. These are same quantity. So, V cos mu as v plus dv cos mu plus d theta. Okay, which I expand as the following: cos mu cos d theta minus sin mu sin d theta from our basic trigonometric relation. So, I expand this further: v cos mu cos d theta minus v sin mu sin d theta plus dv into cos mu cos d theta minus dv sin mu sin d theta. Okay, I just expanded this brackets. Now I will assume d theta is very small. We have already assumed that when we decided this angle is mu. Okay. So, if I assume this, my sin d theta is d theta and cos d theta is 1, and if I substitute that in here, I would get v cos mu equals v cos mu into 1, my d theta is 1, minus v sin mu into d theta plus dv into cos mu into 1 minus dv into d theta into sin mu. Okay. So, I can cancel these two quantities and dv into d theta approaches 0 because both are dv and d theta are small quantities. So, that would multiplication of that would go to 0. So, we are left with these two quantities, and you would end up with this particular relation: d theta equals cos mu by sin mu into dv by v. Okay. So, I just taken d theta here and rearrange these terms, these two terms. Okay. So, this is nothing but cot mu and dv by v. Okay. Now, we also know because mu is our Mach angle. So, you assumed this theta to be very small, and this mu, this shock angle or the wave angle approaches Mach angle. So, I can write sin mu equals 1 by m, which essentially means, so your opposite side is 1 and your hypotenuse is m. So, if I draw a triangle, with hypotenuse m, opposite side 1, and this is my angle mu, this is m square minus 1, okay, which essentially means my cot mu is root of m square minus 1. Okay. I substitute this in that equation for d theta. So, my d theta is cot mu, which is now m square minus 1 into dv by v. Now, I am going to substitute dv by v in terms of Mach number. Okay. So, that is all what I am going to do. So, if I do that, I get the Prandtl-Meyer, so called Prandtl-Meyer function. So, I go back to the continuity equation, differentiate that, get dv by v from that equation, and we start from this particular relation where velocity is Mach number into the velocity of sound. I take log and differentiate, so I would get dv by v equals dm by m equals plus dA by A. From isentropic relation between the stagnation quantity at a state and the static quantity at a state T0 by T, I know it as 1 plus gamma minus 1 by 2 m square, which is also my S0 by A square. So, I differentiate this and get dA by A and substitute in here. So, I get plus minus 1 by 2. So, I get dA by A as minus 1 gamma minus 1 by 2 into 1 plus gamma minus 1 by 2 m square to the power minus 1 into m dm. Yeah. So, I have differentiated this term and I substitute that in here. So, I would get dV by V to be dm minus m minus this quantity, which is gamma minus 1 by 2 into 1 plus gamma minus 1 by 2 m square to the power minus 1 into m dm. Which after some rearrangement I can after some algebra I can get dV by V to be 1 plus gamma minus 1 by 2 m square into dm by m. Okay. So, this is my equation 2. And I substitute 1 in 2. which means my d theta is root of 1 minus m square into dv by v is 1 by 1 plus gamma minus 1 by 2 into m square into dm by m. So, I end up with a relation like this, which is substitute. Okay. Substitute 2 in 1. I get dm by m. So, the integration of this is your so called Prandtl-Meyer function. So, all I do here is that particular one. So, this is the final equation. Okay. If you integrate this, you would get the Prandtl-Meyer function. So, what is important there is your d theta, it is a function of Mach number and your gamma. So, I call this as d nu function of Mach number and gamma. So, your nu integrated over 2 Mach numbers would be a constant, which will be a function of m1, m2 and gamma. That is the idea. So, if I integrate this quantity between nu 1 to nu 2 d nu, okay, is integral m1 to m2 root of m square minus 1 divided by 1 plus gamma minus 1 by 2 m square into dm by m. Okay. So, this can be between nu 1 to nu 2, which is I am writing this from whatever has been done. I am copying it from the notes. Tan inverse gamma minus 1 by gamma plus 1 into m square minus 1 minus tan inverse root of m square minus 1 between the limits m1 and m2. Okay. So, I have a quantity here between nu 1 and nu 2 in terms of m1 and m2. Okay. Or I can write nu as a function of m, this particular quantity, which is gamma plus 1 by gamma minus 1 tan inverse root of gamma minus 1 by gamma plus 1 m square minus 1 minus tan inverse m square minus 1. Okay. So, if I integrate this, I would get this, and I can use it between the limits nu 1 and nu 2, and this particular function is the so called Prandtl-Meyer function. Okay. And if I know my nu 1, if I know nu, what I am talking about is my turn angle here. So, my turn angle is d theta. So, what I have here is d theta is my small turn angle, and if I have a finite value of turn angle d theta, that now depends only on my delta m and r. Okay. Delta m is a function of m1 and which depends only on my m1, m2 and gamma, which we have now defined as nu 1 and nu 2 and gamma. So, this function is nu 1 and nu 2 and gamma. So, my nu 2 minus nu 1 is my delta theta. So, this difference in this function is my turn angle. So, your difference in Prandtl-Meyer function is my turn angle. That is the important thing. And as we have seen, dt is minus for a compression and plus positive for a expansion. Okay. So, your nu 2 is a function of m2 and nu 1 is a function of m1, which will give you your d theta. So, if I know my turn angle, or if I know my Mach number after the turn and Mach number before the turn, I can get the turn angle. So, to demonstrate that, or functions which is now if the quantity now is a function of Mach number alone, nu is a function of Mach number alone. We also know that our Mach angle is a function of Mach number alone. If I can tabulate this, that is what you would see in your gas table as your Prandtl-Meyer function. So, for a given Mach number, I can have mu and the Mach angle. Okay. So, for Mach numbers, I would have different values of mu, and this is what you would see. So, if I have a turn, a finite value of so delta theta is my turn angle, which is, so let us try to find the turn angle. If this Mach number is 1.2 and the final Mach number is 2, okay, m2 is 2, what is the turn angle delta theta? Okay. So, all you need to do is find nu 2, find nu 1, find the difference, and that would be your turn angle theta or delta theta. Okay. So, your nu 2 function of m2 minus nu 1 function of m1 will give the turn angle theta. Okay. So, what does this really mean? When I have a Mach number 1.2, it generates a Mach wave. Okay. This Mach wave is at an angle mu. Associated with this thing, I have a nu which is a function of Mach number alone. Okay. And this generate an expansion wave, with the first one is this and the last one would be nu function of m2. This will have an angle mu angle along with the direction of the so this is my mu. So this is so called shock angle or the wave angle here. So shock angle is only for compression, for an expansion we do not call it as shock angle. So this wave angle is mu, which is the Mach angle, again associated with m2, this is associated with m1. So I have a wave angle mu function of m1, associated with it I have a Prandtl-Meyer function m nu, which is a function of m1, again nu with m2 and mu with m2. Okay. So this difference in this particular function is your turn angle. Okay. So you can also find your mu 2 with your m2, mu 1 with your m1, and hence you can get all the angles that is associated with this particular turn. Okay. So if you look at the tables, mu 2 for Mach number 2 is for gamma 1.4, one in the gas tables book. So nu 2 with Mach m equals 2 is 28.6, and nu 1 with m equals 1.2 is sorry, yeah, it's 26.3, and the other one is 3.55. So your delta theta or theta is this minus this, that will be around 23. Around 23, which means this angle is 23. Okay. Okay. So we will now do some exercise tutorials on Prandtl-Meyer functions.